Hello and welcome back to my channel. I hope everyone is having an amazing day so far. In this video, we're going to go over Boolean operations in set theory. But before we dive into that, let's just do a quick review of what a set is. And I already wrote this out. So a set is a collection of distinct objects. Distinct is a very important word here. So let's take an example. The natural numbers, you should be familiar with it. We often write it as such, which is basically just the number 0, 1, 2, 3, and so on. So every member, or in this case, the members are just numbers. So every member of this set is distinct. There's no duplication. 0, 1, 2, 3. We keep counting on. They're all different. And the next important property of sets is a member, well, an object either is or is not a member of the set. So for example, and I already have this here, but I can write that 2 is a member of the natural numbers. And this symbol right here generally means that 2 is in the natural numbers or 2 is a member of the natural numbers. However, because we're just starting at 0, I can have -2 is not a member of the natural numbers. So that's an important property of sets, is an object either is or is not a member of that set. And here we have numbers, but we can really have any kind of unique objects we want. We can have colors, we can do letters of the alphabet, we can even do emojis, as long as they kind of follow these properties. Next, if all of the members of one set are also members of a different set, we can say that we have a subset. So for example, previously I had the natural numbers. So starting at 0, 1, 2, 3, and so on. But we also have another very common set of the integers, which we annotate like this. And that actually includes the negatives. So we would start at, let's say, so we have -2, -1, and obviously we go all the way back towards -infinity. 0, 1, and 2, and so on. And here I can see that starting at 0, I basically have my natural numbers. So I can see that every member of the natural numbers is also a member of the integers. So here I can write that the natural numbers are a subset of the integers. And there's two common terms. We have a subset and a proper subset. This notation right here is just for a subset, meaning there's a possibility that these two are equal. However, if you know for a fact that the set on the right-hand side has at least one more member than the set on the left, then that's where we have a proper subset, which here we can see we have a proper subset. The natural numbers are a proper subset of the integers because we know for certain, yes, all of the natural numbers are contained in the integers, but we also have more members in the integers that do not belong to the natural numbers. Also, we should go over two very common ways of annotating a set. The first is just in curly braces, which is what we were doing for the natural numbers and the integers. But for example, I can just have some set, I'll call it S, and I can write in my curly braces, list out the members of my set. So let's say I just want a set of 1, 2, 3, and 4. That's one common way of annotating a set. Another, and you'll see this a lot, is called set builder notation. So let's say that I have another set Q, or I'll just write, Q. The way we would write this out, and there's slight variations to this depending on which math book you're looking at, but it's usually the same pattern. We have the member of our set, we'll call it X. We'll either have a pipe or a colon, and this basically means this member X such that we'll usually annotate the larger set that X belongs to. So let's say that X is some member of some larger set X, and then X has some property, and we'll just call it Q. So X such that for X in a larger set X, X has property Q, and here we could see Q would be a subset of this larger X. So for example, we can say, let's say that Q is X such that X belongs to the natural numbers, but it has a property. In this case, let's say and. We'll say x is greater than 5. So this is just a list of the natural numbers or the integers greater than 5, so starting from 6. All right, so that's a quick recap of sets. Let's go ahead and get into Boolean operations. Okay, so for Boolean operations, we're going to start off with a very similar definition for each of these operations. So given a set X and subsets A and B of X, and in this case, we could think of big X. Oftentimes, you'll hear it referred to as a universal set. So let's start with the union. So A union B, in set builder notation, we would read it as X, and let me make sure that you can see that this is the little x, because it's a member, X, such that X is a member of big X, the universal set, where X is a member of A, or, and this is the important word, X is a member of B. So let's do an example. Let's say that I want my universal set, big X, to be the numbers 1, 2, 3, 4, 5, 6, and 7. And let's say A, which here it's going to be a subset of X, is just going to be 1, 2. And B is going to be 2, 3, and 4. So in this case, A union B would just be 1, 2, 3, 4. Because here we were basically saying that X is either in A, which is 1 and 2, or X is in B, which is 2, 3, and 4. And notice how we have the member 2. It's an object in both of these sets. But since we're only allowed to have distinct objects in our set, A union B, we don't need to write that 2 twice. We just write 1, 2, 3, 4. So that is the union between two sets. Okay, next we have another very common Boolean operation. We have the intersection. And here I really just had to change a few symbols around. So now we have a different symbol. So for intersection, it's basically like the upside down union. So A intersect B is X such that X is in the universal set X, where X is a member of A and X is a member of B. Here I only had to change one word. I just had to change the or to an and I'll use the same sets from the previous example. So we have X is 1, 2, 3, 4, 5, 6, 7. A is just 1, 2, and then B is just 2, 3, 4. So we want to find A intersect B, and we're looking for values in A where basically for some X in A, some member of A has to also be a member of B. And in this case, the only real value that we have here is just 2. So this is the only shared member between these two sets. So we would just write, this is just a set with one object, and it is 2. Also, something interesting to note, hypothetically, if B did not have this 2 here, so if B was just the set 3 and 4, then this would just be an empty set because there is no X that is in A and that is also in B. So that's another fun little property of intersections. Okay, for our next Boolean operation, we have the complement, and we'll write it this way with set builder notation. A complement, you'll usually see it as the set with a C. Sometimes you'll see it A with a little line, but these both generally mean A complement. So we read it like this: X such that X is a member of big X, once again, our universal set, and X is not a member of A. So using the same sets we've been using this whole time, my universal set, big X, is 1, 2, 3, 4, 5, 6, 7. A is still just 1, 2. So X is a member of the universal set X, but X is not in A. So from these, we're basically just going to eliminate the values in A. So we're just going to take the universal set, but remove the values that we had in A. And we would write this like this. So A complement, in this case, since A is 1, 2, A complement would just be 3, and let me write this a little better. 3, 4, 5, 6, and 7. So these are basically the members where X is in the universal set X, but X is not a member of A, which is just 1 and 2. Okay, and the last Boolean operation that we have is the difference. This one's written a little bit differently. We usually write it with the minus sign, so we say A difference B is X, such that X is a member of big X, the universal set, where X is a member of A and X is not a member of B. So let's use the same sets we've been working with. We have our universal set 1 through 7. A is just 1 and 2, and B is 2, 3, and 4. So X is a member of A, so we have 1 and 2, but X is not a member of B, which is 2, 3, and 4. Here, remember, we have a shared value, which is 2. We don't want any members that are in B, and in this case, since 2 is a member of B, we have to leave that out of our difference. So we would write A difference B, in this case, as just 1. Because 1 is basically the member of A that is not also a member of B. And we can also reverse this. So let's say we wanted to do B difference A. So now we're looking at members of B that are not members of A. And in this case, once again, we would just leave out that 2, and we would just have 3 and 4. Okay, so these were some basic Boolean operations in set theory. Boolean operations are incredibly useful. You see these a lot in applications of science, computer science, and so on. But I hope this video helped. If you have any questions, comments, suggestions for how I could have made this better, I'd love to read about it in the comments section. But I just want to say thank you so much for taking the time to watch this video, and I hope you have an awesome day. I'll see you next time. Take care.